Okay, we are just using all these formulas. We are now going to do some calculation on electric field. Okay, calculate the electric field strength at 8 millimeter from 4 microcoulomb charged particle. Right? Just memorize the formula. Put in your value. You can use K if you want to. Right? Change it to coulomb. Change it to meter. So you should be able to get 5.62 times 10 to the power 9 Newton. Can?
Okay.
Good. 2-point charges, 4 microcoulomb, 6 microcoulomb, 20 cm apart. Calculate the electric field strength at the midpoint between the two charges. That's the midpoint there. 10 millimeter from the 4 microcoulomb charge. Okay, due to this 6 one, that's your E2. Due to this 4 one, that's your E1. And remember, both are vectors. Electric field is vectors. Right? So that's the formula to calculate the electric field. Take direction to the right as positive. It's a vector. You have to choose a direction. Right? Due to the 4 microcoulomb, that's your E1. Okay, calculate out. Due to 6 microcoulomb, same formula, right? But it's negative because it's to the left. Calculate out. And add them up. Right? Reaction 2 is vector quantity, add them up. You get negative, that means it's to the left. Can? Okay, good. The neutral point from 4.0, neutral point is where the electric field is 0 lah. At neutral point, the resultant electric field is 0. Both fields are equal but in opposite direction. Right, same. 4 microcoulomb and 6 microcoulomb, 20 millimeter apart. So we calculate from X. From the 4 microcoulomb, let it be X. Electric field due to 4 microcoulomb. This one, you don't need a value. So we don't need to calculate, put in the real value of K in and then calculate out, no need to. Right? You want to, you can, but it's unnecessary that you cancel off anyway. Then 6 microcoulomb. Right? 6K. So both of them are in opposite direction. So they are, for it to be 0, both of them must be equal. And cancel the K. Cancel by 4, this is 1, cancel by 4 is 1.5 here. Take X squared across, take 20 minus X across, and square root it. Okay. We choose a positive one now. Can or not? Okay, you won't bother about this one. You can try that yourself. Okay, page 126. Electric potential. I must follow the syllabus. Define electric potential at a point as the work done per unit positive charge in bringing a small positive charge from infinity to the point. Recall and use the fact that electric field strength at the point is equal to the negative of potential gradient at that point. Then use this formula. of electric potential in the field due to a point charge, and understand how the concept of electric potential leads to electric potential energy of 2 point charges as that. Okay, electric potential. Electric field is a vector, and addition by parallelogram or triangle law is more complex. A lot of work, a lot of calculation involved. When describing a field, potential is usually a more useful quantity than an electric field because it's a scalar quantity and can be added directly when more than one field is in concern. Right? Due to many charges, then you have more than one field. Yeah, each charge contribute to their own field. So potential is more useful quantity to calculate. Okay, we define potential, define electric potential at the point. Is the work done per unit positive charge in bringing a small test positive charge from infinity to a point. The potential at infinity is zero. Because the force on the charge far away from one another is zero. So potential at infinity is zero. Potential at the point due to a charge. There's your charge. Potential P at a point P, a distance r from the positive charge Q. Right? There's your charge, positive charge. You're interested in a point P. What's the potential here? The distance is r. So you just need to memorize the formula. Right? It's given in the formula sheet. You know how to use it. No derivation, but know how to use it. Right? That's the electric field line. So at point P, that's the electric field. This is the potential energy per unit charge. Right? It's work done per unit charge, so it's potential energy per unit charge. So potential energy is just EP equals to VQ, where Q is a test charge. Right? You put a test charge here, and potential energy is EP is VQ. Right? Know how to use it. That's your electric field of a point charge, point positive charge. At the same distance from the charge, the potential is equal. Right? Same distance, same charge, potential is the same. So it's a sphere. It's sphere. Not uniform, right? So not equal distance apart. The concentric circle are not equal distance apart. Right? Further and further, they become weaker and weaker. Right? According to here. Right? Know how to use it. Formula in the data sheet. Okay. Quite common to ask you to draw. Right? Potential of a spherical conductor is uniform, the same throughout the sphere. Right? It's a V naught at R. So it's like gravitational field. It's 1 over R. So you divide by half rho, divide by 2 rho, 2R divided by 2. If the potential is V naught, the charge will be distributed evenly on the spherical surface. Right? Electric field is zero, potential is the same. So that's why the charge doesn't move anymore. The sphere becomes an equal potential volume, same everywhere in the conductor. Right? That's why we draw a point there. And half of it, right? 2R is half of it, 3R is 1/3 of it, right? 1/3. 4R is a quarter of it, divided by 4. Okay, make sure you know how to draw the curve. Can
Mm.
no need to do all this. But if you want, you can draw a table. Electric potential energy. Know how to use the formula? Electric potential energy is stored energy that can do work. Potential at point P, the distance r from Q is given by this equation, right? Due to this charge, the potential at P is given by that. We are just using our definition of potential different, right? So just cross multiply, potential different, this is the work done. The potential energy of a charge Q placed at P, we place a test charge there, Q, so it becomes this potential times Q. It's given a data sheet now to use it. Okay or not? Stop me if I'm going too fast. Right? That's the electric field strength of a point positive charge Q at a distance r away. Q is the point charge, r is the distance from the charge. Electric field strength points to lower potential. Right? As you go further and further, the potential decreases and is perpendicular to the equal potential surface. Right? These are equal potential surface. That means the potential on this surface are all the same because they are all a distance r away. Right? They are spheres. Right? That's the formula for potential. Okay. Between the relationship between E and V, right, you need to recall and use. That is, we differentiate. Differentiate this one. You get that? Right? That equation there, you differentiate that. So it's called electric field strength equals to minus potential gradient. Negative as R increases, V decreases. For constant field, right? For constant field, we have that is constant. R is constant. So that is our formula that we use it. Right? We didn't derive it, we use it. Right? Parallel conducting plate. Okay, you won't bother deriving it. If you want, you can look at my electron volt. Just reminding you, 1 electron volt is the energy an electron acquire in accelerating through a potential of 1 volt. That is a unit of energy. Right? When working with energy of nuclear particles of, for instance, electron and proton, the energy involved is very small, or 10 to the power minus 19 joule. So electron volt allow us a convenient way of writing the magnitude of energy, right? Which is about 10, 20, 11.5, 1.3, something like that, rather than always 10 to the power minus 19. One electron volt is 1.6 and 10 to the power minus 19 joule. Right? Memorize it. Same as electron. The value is same as electron, but it's in joule. Right? It's not given a data sheet. And electron accelerate to a potential difference of 5 volt will gain a potential difference of 5 electron volt. Electron accelerate to a potential difference of 20 kilo electron volt will gain a potential difference of 20 kilo electron volt. Right? We are just using this formula. Right? If we use 5 volt times charge on the electron, then you get it in joule. But if you remove the electron, then it becomes 5 electron volt. Okay or not? Okay, try this question. An electron in an electron gun of a TV picture is accelerated to a potential difference of 2.5 kilovolt. the gain in kinetic energy by electron volt in joule. Right? Gain in kinetic energy 2.5 kilovolt becomes 2.5 kilo electron volt. Right? When you convert it, it's VQ. V is 2.5 kilo electron volt times your is electron. So it's 1.6 and 10 to the power 19. Get that? Can get the answer?
Yes, got it.
The final velocity of electron, assuming was initially at rest. Right? So the electron is accelerated to at rest by 2.5 kilo electron volt. So we just use EK is half mv squared, and this is the energy. Right? This is the mass of electron, can get from data sheet. Okay, any comment? Anything not clear?
Okay.
Right? This is for your information. Won't be in the syllabus anymore. Last time it was in the syllabus. Comparing gravitational electric field. Right? Gravitational field, the field is created by a mass. Electric field, created by a charge. Electric field strength we define as G, force per unit test mass, force per unit test charge. Near the Earth's surface, G is constant, whereas this one is all pointing toward the Earth's surface. This one for the positive charge infinitely plane charge conductor is parallel, uniform. Field is attractive, right? Because the force is attractive. Whereas this one can be due to positive or negative charge, so it can be repulsive for positive charge and attractive for negative charge. Similarity, both have force formula is 1 over r squared. Potential is 1 over r, proportional to 1 over r. Difference, gravitational force always attractive. Electric force can be attractive, can be repulsive, depending on whether it's light charges or unlike charges. It's just for info only. You don't need to learn. Okay, the rest I will leave you to read yourself lah. Better to do solve problem lah. Okay. The rest are just for info lah. Some of them are for info, like Boy's planetary model. Right? Just for info. So these one just to help you lah. All the formulas that you need to remember. What are things are given. Right? Negative potential gradient electric field. There's your test charge. There's your K. There's your epsilon. Right? If effect of medium other than air is just to modify this one, no? Right? Modify this one, but we are not interested in that. Okay, let's try some example. Okay, just to clarify for you, right? For electric field, it won't come out lah, because this is basically a lot of calculation involved, and basically it's AS work, B or A2 plus AS work. So it doesn't show anything. Okay, so anyway, due to this 5 nano coulomb, that this is the electric field. Due to this -4, right? Minus the electric field is going towards A. Right? There's the electric field. Then complete the parallelogram, find the resultant electric field. Right? It's a lot of calculation. So just to illustrate to you, potential is easier to calculate. Right? You're just using this formula, that's all. So it's easier. Right? 5 nanocoulomb minus 4 nanocoulomb, 8 cm apart, is 6 cm, that's 10 cm. Potential at B due to charge at A, this one. Right? But you have to consider the negative charge. Negative charge there, value, calculate out, negative value, right? Due to C, right? It's positive charge. So I put positive value, calculate out, 750. The resultant potential, you just add them up, add these two up together, it's positive. Anything not clear? Okay, we are happy with that. Let's carry on. Alpha particle of energy 5 mega electron volt is incident on a gold nucleus of atomic number 79. Determine the distance of closest approach. Closest approach, both of them are positive charge. Gold nucleus is stationary, alpha is shooting, so the speed will start to decrease until the energy becomes zero. That's the distance of closest approach. So 1 electron volt is 1.6 and 10 to the power minus 19 joule. That's the energy that you have to convert it to joule. 5 mega electron volt is 5.6 and 10 to 1.6 and 10 to the power minus 19. Calculate out is 8.0 and 10 to the power minus 13 joule. We use this formula. The alpha particle will lose kinetic energy as it gains potential energy. So this is your kinetic energy. This one, potential energy. 79 electron. This is a charge on the electron. Right? One is alpha. Alpha has two electrons. Gold has 79. That's why there's a square there. It's the same 1.6 at the power minus 19. And then this is your epsilon. That's your R. Okay with that? Okay, let's try some graph. Let's try this question. Define electric potential at a point. Memory work. Easy score point if you remember your work. Can remember?
Oh, this one AS answer also can, right?
Say again.
Oh, no. Oh, yeah.
This A2 work, not AS. Can remember the definition for electric potential? We just have one period. Yep. Work done per unit positive charge. Moving the positive test charge from infinity to the point. Memorize. Two isolate point charges, A and B, are separated by 30 cm as shown in figure 5.1. Charge at A is 3.6 and 10 to the power minus 19 coulomb. Right, that's the graph that's given. Right, that's the equation for potential difference that you can get from a formula sheet. State with reason whether the charges are like or unlike. Remember, this is a potential graph. Like or unlike?
Unlike.
Unlike, good. Right? One is positive, one is negative charge. Positive charge is this one, positive potential. Negative charge is negative potential. What does the gradient represent? If it's electric field, both are in the same direction. If it's unlike charges. What does the gradient represent?
Uh, shit.
Haven't got into your head
Electric
yet.
field.
Good. Minus electric field. Right? That's the
Oh,
equation.
minus electric field.
Minus electric field. Unless they want magnitude. Either you put negative here, the gradient, or minus here. Since they ask you the gradient is minus electric field. How would the electric field strength graph looks like? Yep. This is just basically using your gradient. Gradient. All the gradient are negative. Right? But because of the negative, negative becomes positive. And then that part will be 0. Then after that, this is maximum. That is maximum, but this point is greater slope than this point there. Right? So there's a positive charge, there's a negative charge. So that's how it looks like. Roughly, we are asked to sketch. There's your 18 here. There's your 5. There's your 27. Can.
Mm.
Okay, let's answer the question paper. The variation with distance x from A along AB. Right? That's your A, charge A. That's along AB. Oh, the potential is shown in figure, this is figure 4.2. State the value of x at which the potential is 0, reading from the graph only. What is the value? Yep, where the potential is 0.
That shows. Uh, wait.
10 minutes left.
18 17, 18, 18.
18 there lah. Use your answer in 1 to determine the charge at B. Right? Read the graph. Simple. Next one, use the formula. Right? Charge at B is a negative charge. Potential at that point is due to the both charges. Right? You can use one charges. Right? For both charges, one is A, one is B. So both of them are 0. Right? B is 0. So QAR, right? This is equal. Right? That one will cancel off. So QAR2, Q1, QBR1. Put in your value. Right? That's 18 cm. That's 18 cm R1. R2 is 30 minus 18. Right? As long as they are the same unit, yeah, all right. No need to change to SI unit. Can.
Mm.
Just repeating. A small test charge is now moved along the line AB from 5 cm, that's your 5 cm, to 27 cm, 27 cm here. Say and explain the value of x at which the force on the test charge will be maximum. Yep. What is your answer? Here, slope. Say I explain the value of x at which the force and electric field strength is the same. Electric field strength is the force on the unit charge. So the slope, the gradient is electric field strength. So electric field strength is maximum here or maximum here. Largest will be here because the slope is greater.
Oh, okay.
Force is charge times electric field strength. Largest at 27 cm here, as the gradient is the steepest. Can. Okay. Same definition, memory work. Two spherical charges P and Q may be assumed to be point charges located at their centers. The particles are in vacuum. Particle P is a fixed position. Particle Q is moved along the line joining the two charges as illustrated in the figure. The variation with x of the electric potential Vp of Q is shown. Q is the one that is moving. P is the one that is fixed in position. Do you want another class or we call it a day? Yep.
A bit tired also.
Very tired. Then we just finish up with this one. Okay,
Okay.
that's the graph. State how the magnitude of the electric field strength is related to the potential gradient. Yep. Memory work. Oh. Memorize work. Electric field strength is equal to the potential gradient. Or negative, they want magnitude. Magnitude, we don't worry about the negative side. Okay. Right. That's the equation. Use your answer in one to show that the force at Q is proportional to gradient of the curve in figure 4.2. Electric field strength is proportional to force on charge Q as the potential gradient is proportional to the gradient of potential energy graph. So the force is proportional to the gradient of the graph. Look. Yep. You can treat this as potential is the same. Can?
Yeah.
Magnitude of charge on each of the particle P and Q is 1.6 and 10 to the power minus 19 Coulomb. Calculate the separation of the particle at point where particle Q has electric field strength of 5.1 electron volt. Right? That's the energy. Convert it to joule and use the equation. That's the energy, potential energy. Right? Both are electron. So the square there, this is 4 pi epsilon naught times R. Okay, can?
Mm.
By reference to figure 4.2, state and explain whether the two charges are the same or opposite sign. Yep.
Mm.
Is it
Uh,
two charges have the same or opposite sign?
Opposite.
Work is got out as x decreases, so opposite sign. No? And we need to explain, not just say opposite, you just get 1 mark only. The effect, if any, on the shape of the graph of doubling the charge on P, on particle P. Right? Play with the formula only. Yep. Increase. Oh? Energy would, that's the formula. Right? Increase one of them, you increase the potential energy. So it's that way. Energy will be double. So gradient will be increased. Gradient of graph is equal to the force between the charges. Right? That's your AS work. Work, force times distance. So the gradient is the force for energy graph. Yep. Can.
Mm.
Okay, we won't be able to finish this, but you can try it. And then we will try to answer it in our next lesson. Two small charged metal, sphere A and B, are situated in vacuum. The distance between the centers are 12 cm. The charge on each sphere may be assumed to be a point charge at the center of the sphere. Point charge is movable. Right? Because the point charge is point P is movable. That lies on the line joining the centers of the sphere and the distance x. X is from sphere A, the center of sphere A. Variation with x of the electric field strength and point as shown in 4.2. Right? For light charges, this is the electric field strength. They are both in different direction. That's why it can be positive, can be negative. Positive on this side, negative on that side there. Right? That's why it looks that way.